Hello YouTube, my name is Matthew and today I will be going over a problem that involves chemistry, and I will give you a warning that I may make incorrect statements, so I encourage you to look up things on your own as far as definitions or terminologies. So we'll start with this problem in exercise 3 on ChemWiki. It says, in the exercise in example 13, you calculated Kp equals 2.2 times 10 to the 12 for the reaction of NO with O2 to give NO2 at 25 degrees Celsius. Use the delta H of formation values in the exercise in example 10 to calculate Kp for this reaction at 1000 degrees Celsius. So Kp is equilibrium constant in terms of pressures, and as you can see in our reaction we have gases which can only exert pressures. And so on ChemWiki they refer to as example 13, example 10. I looked on there and they didn't actually give me the heat of the enthalpy of formation for this problem, so I took matters into my own hands and I had to Google them. But anyways, let's proceed. So we have our reaction here. It is balanced, and so if we go down, I have written down the given information, and so we have the equilibrium constant for pressures at this temperature, and they asked to find the equilibrium constant of pressures Kp for this temperature. And so this number here is very large, so you know that it favors the products. So reactants to products, it favors the products because it's a very, very large number. And that's at a very lower temperature than this. So we'll see how this comes out to be in the end. And so how can we find this value? Well, we have this equation here. They call this Capron equation, which is very, very commonly used throughout many chemistry problems when involving two temperatures or two of any one thing. And so we have this R is just a given value. It's expressed in joules per mole K. It's for energy, and the problem they asks us to use the heat of formation to find this value. And so this all relates, everything that we've given or needed relates to this equation here, so we can solve for one of the K values. And so if you go down here, we're missing this value here though, and it's in here. And so how we can find this is how they asked us to use the heat of formation. And so we know that this is the known information, that delta H at standard, this symbol here means standard conditions, equals the products minus the answers, the formation, excuse me. And so as we move down, we have our reaction, and this is from Google. I found these values because they weren't in the ChemWiki. And so we have these expressed in joules, kilojoules per mole K, and this is 0 because this is an element in its natural state, which means you don't have any energy of formation for that. It's 0. It's just as defined elements in their natural state. They do not have any energy for formation of them. And so we now have many values, so we can calculate our delta H as they asked us to using the formation. So we have these units canceling out here. So this cancels out with that, so that we have the products minus the reactants. And so these values came from our balanced equation, the 2 moles of this NO gas and 2 moles of this NO2 gas. And so we are able to get our value, but it's expressed in kilojoules per mole. So I converted it using this conversion factor. Every kilo is 10 to the 3 units, so it comes out to this large number, and it's negative, which tells us it's exothermic. So the change delta change in heat or energy enthalpy, I believe, is exothermic. And so as we move down, now we have this value for our equation. So we have everything that we need, and we just need to solve for one of the K's. To make it more convenient, we can solve for K2, and this K2 corresponds to the T2, and this K1 corresponds to the T1. And so we move down and we have our equation. We can use log rules to separate these values so we can solve for K2, or you can just simply and that's continuing of solving for this K2, and then next you would exponential both sides to get rid of the ln, but I went ahead and left it in this form, and I was just going to solve for this here. And so I brought the values back down here so that we can plug them in. And so we move down to here, and I plugged in everything. The units cancel out. These temperatures are expressed in Kelvin so that it can cancel out with this constant, this 8.314 constant that's given to us. It never changes. And so after plugging this into your calculator, you should get this. And it's not expressed in units because everything canceled out. And so you still have your fraction, your logarithm fraction. And so after exponential both sides to get rid of this ln here, you now have this equation here. And so if you solve for this, you will get this number here. You should get it. Double checking your calculators, and then we just use basic algebra. You multiply both sides by this number here to get K2 by itself, and this should be your answer. Now this is not the correct answer that they have on the ChemWiki, but I believe they were referring to some nitrogen compound, some other nitrogen, I think ammonia compound, and so they gave a different answer on there for the correct answer. This is exercise 3 on ChemWiki. And so this value, remember I said that we can compare it to the larger value at the small temperature. So when we raise the temperature, the value of K, the constant Kp, is smaller now, which tells us that it favors the reactants over the products, versus when it was this large, it favored the products over the reactants. And so this is your final answer, and I encourage you to go through all this work and double check and look up definitions if I mispronounce anything. Here's a glance at the work one more time, and I hope this has enlightened you and as far as chemistry and chemical reactions and what have you. And my name is Matthew again, and hope this helps one of you out. Thank you.